Okay, more on connectivity. So if I've got a path, a UV path, then I will say that the vertex U and the vertex V are connected. We can say U is connected to V, V is connected to U. It's a symmetric relationship, so I'm really not going to worry about which is the start and end here. Connection in this case is both directions. A whole graph is connected if every pair of vertices in it is connected. But clearly, not every graph is connected. But that means if a graph is not connected, it's going to have parts. Here's a graph. I haven't labeled it. I just made it up just now. But here's my graph. It's got two connected subgraphs, right? There's this piece, that's a subgraph that's connected. And there's this piece that's a subgraph connected. Now that's a big as a connected piece as we can get in each of those cases. Those are called components. Now that's a really windy way to say maximal. A connected subgraph that is not a proper subgraph of some other subgraph. That sounds really stupid. No, I mean, this is as big as you can get without becoming disconnected. So this graph has two components. We're going to say K of G is the number of components of G. So in my case, K of G is 2. If my graph is connected, K of G is 1. Typically, we'll name the components somehow. Usually they're numbered. Like I would have G1 and G2 being the components of this graph, G. You could call them H and K if you wanted to. You could call them anything you wanted, but it's usually the name of the graph and then a subscript for the pieces of. Questions? Chapter 9 from the discrete book, I'm going to define a relation on vertices. Two vertices are related if they're connected. We had a lot of properties of relations back in discrete. Anybody remember any of them? Bingo. Those are exactly the properties I'm after. And if a relation is reflexive and symmetric and transitive, we call it equivalence relation. I claim this is an equivalence relation. That should be a really direct proof. Is every vertex related to itself? Can I get here from here? I don't have to go anywhere. That was easy. That's a trivial walk. I like that. So it's reflexive. If U is related to V, is V related to U? Well, if U is connected to V, then V is connected to U. I just take the same path and turn it around. Sorry, the same walk and turn it around. Is it transitive? How?
If you have like some third element W that V is connected, you have like U to V and V to W.
So I can get from U to W, right? And I get a walk from U to W because when I connect paths, I don't always get a path, but I still get a walk from U to W. That's perfect. And if I can get a walk, I can get a path. We discovered on Wednesday. As long as I have a walk, I have a path. So I know I can have a path from U to W. Even though when I join the two paths, U to V, V to W, I might not get a path. I can then smaller reduce that to a path. Okay, wait a second. When I have an equivalence class, I automatically get something else. On the set of vertices. A set is countably infinite if I can make a bijection between it and the natural numbers. I haven't done any bijections here at all, so I'm not to count. And I really don't want to deal with infinite graphs. We can, I don't want to do it. This course will not address infinite graphs. What do I get from every equivalence relation just by the fact that I have an equivalence relation? We did this in chapter 4 in discrete, chapter 5, and chapter 9. And we did it yesterday in abstract. You have your discrete books online still somewhere? Books available are mateys. The books in the Math Enrichment Center. You should refresh yourself a bit. What do we get from every equivalence relation? In the very first Wikipedia article on equivalence relations too. Yeah, I'm sorry, I misspoke. We did it Tuesday, not yesterday. But we did it in abstract. this week, which means you did it a while ago. Every equivalence relation makes equivalence classes, and that partitions my set into separate, non-overlapping pieces. Exactly what we called components above. Each component of my graph is an equivalence class under this relation, which means there was another way to prove this was an equivalence relation, was to show that this relation is exactly the relation defined by that partition up there. Every partition gives me an equivalence relation. Every equivalence relation gives me a partition. I have a partition, I must have an equivalence relation. Each vertex, each edge within my graph can belong to at most one component. Got to be in there somewhere, but the components are disjoint because they're the cells, they're the classes in my equivalence relation. They can't overlap at all. If I have a disconnected graph that is not one big component, then there has to be at least one pair of vertices where there's no edge. If you pick two vertices and they're in different components, there can be no path between them. No walk, no trail. In one sense, connectedness is a visual picture. Is this one blob or multiple blobs, right? But what's a method by which I think about actually determining computationally from the lists somehow as to whether or not something is connected? That's not intuitively obvious. So it turns out that there are a couple of nice proofs, theorems that we can write about the way in which we determine whether or not a graph is connected. A bunch of that is looking at subgraphs. So in one sense, this is almost inductive. In another sense, it's kind of recursive. I build down instead of building up. I want to walk you through one of them because this particular proof is sort of a model of how we'll do proofs a lot in a class like this. This happens to be a direct proof. So I didn't think I'd start with anything psychotic. This statement of this theorem reads kind of strange. Let G be a graph of order at least 3 if G contains two distinct vertices, U and V, so that G take away U and G take away V are each connected, then G is also connected. Okay, wait a second. Order at least 3 means what? Right, order is number of vertices. So I have to have at least 3 vertices. And I have to be able to name 2 of them, pull one of them away, the result is still connected. I put that back, I pull the other one away, the result is still connected. With both of them in there, it needs to be connected. All right, this is an if-then. If we have 2 distinct, let's do this as a direct proof. We're going to work the if-then straight through. Suppose all of that garbage is true. G is a graph of order at least 3 and has 2 distinct vertices U and V, so that G minus U and G minus V are each connected. So that's where I'm starting. I want to show G is connected, right? I want to show that G itself is connected. Definition of being connected is I can pick any 2 vertices and there's a path between them, right? So I'm going to pick 2 vertices. Now, it is possible, since I am picking any 2 vertices out of this whole graph, that I happen to pick U and V. That would suck, wouldn't it? So let's start with that not being the case. So case number 1, I didn't pick both U and V. I could have picked one of them, I could have picked the other, but I didn't pick them both. Without loss of generality, ooh, I'm really digging out all the crap from discrete. I'm going to say the one I didn't pick was U. Without loss of generality, assume U is not in set X and Y. V maybe, but U is definitely not. Well, then wait a minute. I know that X and Y are both part of a different graph that's already listed up there. If U is neither X nor Y, then X and Y are 2 vertices in the graph G take away U. What does that mean? What information does that give me that is beneficial at this point? Right, but it could be even more, right? I don't know how many vertices G has. It's got at least 3. But it might have 75, right? but I know it doesn't have U. What's special about G minus U? It's connected. Wait a minute. G minus U is connected. What's that mean? What's the fact that G minus U is connected? Tell me. About X and Y. There's not just a walk, there's a path. Because they're part of a connected graph, there's got to be a path. There's an XY path in G minus U. So there's a path from X to Y that never touches U nor any of the edges in G that are connected to U, right? It avoids U and the neighboring adjacent edges of U. But all of the edges then are in G, aren't they? If they're edges in G minus U, then they're also edges in G. If they're vertices in G minus U, they're also vertices in G. That means that this path is in G as well. There's an XY path in G minus U. Call it P. P is also an XY path in G. So I picked two arbitrary vertices, X and Y, and they're connected. What does that tell me about G? That's exactly correct. The arbitrary vertices means that G as a whole must be connected. Check mark. But, and it is not a small but, that's case 1. What's case 2? But that would simply be, if I change that without loss of generality, V is not an XY. That would be the exact same argument, and that's why I did it without the loss of generality. So you could swap all the U's and all the V's from here down, and this argument would still be the same. Aha. I could have been unlucky in my selection, and I could have picked both U and V. Start. Which means there's another part to this where now I have to say, well, what do I do now? So, case 2. I picked U and V. All right, crap. Flip a coin. Is X U or is X V? It really doesn't matter, does it? So again, without loss of generality, I am no longer going to think about X and Y. I'm going to think about U and V. How can you guarantee me that I can get from U to V? Because that's the goal. I have to be able to create a path from X to Y. I have X, Y, I have U and V. I have to be able to create a path from U to V. How do you know I can create a path from U to V? What's connected? Go back to the hypothesis that I wrote in the start of my proof. My goal is to show that G is connected. Can't start with that. I'd be arguing myself in a circle, Abigail. But that's my eventual conclusion. I want to get to G is connected. What do I know is connected to start with? Okay, G minus U is connected. G minus V is connected. So how can I use those to get from U to V? The rest of you are allowed to talk too.
Because the graph is ordered.
Yes, but how do I know it connects them together? There has to be at least one other vertex, right? There's got it. So let's name our third vertex. I'll actually write it down. I'll say, hey, wait a minute. Since G is of order at least 3, there exists W in the vertices. W is not U, W is not V. I have a third place, W. By the way, you can use whatever bloody names you want. I'm playing the same game I always play. Variables come from the end of the alphabet. What do I do with W? In G minus U, there's a path from W to V. In G minus V, there's a path from W to U. G minus U is connected. In G minus U, there exists a path P1 from V to W. Yes, from V to W. In G minus V, there's a path from W to U. So I have path 1 in G minus U. I have path 2 in G minus V. Now what, Reese? Except that new thing is now, it's in all of G, and it's a walk, not a path, right? When you do paths together, you might end up repeating edges or vertices or something, so that only becomes a walk. P1 union P2. P1 followed by P2, P1 plus, I don't know what the right notation would be here. If I think of them as ordered lists, I just want to concatenate them together, right? P1 union P2 is a VU walk. Not a path, but a walk. But what did we prove, or at least walk ourselves through the proof of on Wednesday? And there's a walk. There must be a path. Walks are allowed to repeat things, right? So I take out all the repeated backs and forths, all the loops, just chop them out, and I get a shorter path. Is a VU walk right up here, right in G. Sorry, I forgot to specify that. Because we moved from being in G to minus U or G minus V to being in the whole graph, so I could get both U and V in there at the same time. Hey, wait a minute. That means X and Y. I said I wasn't going to talk about that anymore. U and V are connected to each other, right? If I can connect U and V, then my graph must be connected. In both cases, I ended with the same sentence. Graph must be connected. My graph must be connected then, regardless of whether I picked U and V or not. Whew. Why did I need at least an order of 3? Or it wouldn't even have anything, right? Here are my 2 vertices. I take it away, that's connected. I take it away, that's connected. That's not connected. Without that other place to go, without W, I can't do this argument. And that's the piece that would only work if I had at least 3 vertices. Questions? As in discrete, as in linear, as in intro to theoretical, all of the proofs we are doing at this point either build on other things we've already proved here or the definitions we are using to write those concepts. I'm not pulling weird analysis or derivative techniques out here. I'm not suddenly saying, because of this thing we know from linear algebra, right now, at this point in time, this course is self-contained. We're using direct, indirect, proof ideas, and only, at the moment, these definitions. Eventually, I'll connect this to some other courses, but I got to wait. My graph is connected. Pick any 2 vertices, there's a path between them. Please notice that existential quantifier says there is. There could be more than one, right? Oh. If there are more paths, then I think it would be best to try and find the shortest one. Yes? We're going to call the distance between two vertices, the length of the shortest possible path. And I'll call that d of uv, or d sub g, or the distance in the graph g, is the smallest length of any uv path. So if I tell you that the distance between two vertices is 5, then the smallest path between them has length 5. No smaller path exists. If I tell you the distance between them is 2, then you go from U to W, W to V, that's the shortest possible path around. We're going to call those geodesics. The shortest path between 2 points is a geodesic. 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 Now, I know those of you that have been doing a lot of math go, wait a minute, the shortest distance between 2 points is a straight line. It's only true on the plane in Euclidean geometry. The shortest distance between New York and London is a circle. It's part of a great circle around the surface of the Earth. Not flat. Rules of geometry aren't the same. I'm living on a graph that's a bunch of dots with arbitrarily defined connections between them. Straight lines don't even necessarily exist. So let's suppose we had a UV geodesic and it looked like this. V0, V1, V2 up to Vk, where U is equal to V0 and Vk is equal to V. This is my shortest path. Well, this is a shortest length path between U and V. Again, a geodesic might not be unique. That's a claim. I claim the distance from V0 to any of those other vertices must be the same as the subscript. Why is that true? This again is an informal argument, not quite a proof, but kind of a hand-wavy argument for the moment. let's suppose the distance from V0 to V2 was different than 2. If it's longer than 2, then this is not a geodesic, is it? If it's smaller than 2, it's got to be 1, and that means that I go directly from V0 to V2. Why is V1 in a geodesic? This has to be true for every single one of these, all the way up to VK. If I'm starting with a geodesic, not only is that the shortest distance to V, it's the shortest distance to every other stop along the road to V. If U and V are directly connected, if they have a single edge between them, then the distance is 1. If U and V are the same, then the distance is 0. If you have a graph of order n, then the biggest possible distance is n minus 1. Here's a graph. I'm going to steal it from the textbook again. Figure 19. Here we go. Here's a graph. Now, they've clearly indicated one of the vertices, right? So tell me, what vertices are distance 1 from that vertex T? U and X. How about distance 2? Y, Q, R, and V. Distance 3. I can keep building these, right? Have any of you ever played with those metal puzzles, a bunch of different rings and links, and the goal is to get one ring off of the other things? Maybe not. Imagine these are beads connected by pieces of string. I want you to pick up T. If all of those strings are the same length, then everything will fall in layers based on its distance. There you go. Distance 1, distance 2, distance 3. Now that's from T. I could pick a different starting point, right? I could say, let's start from U, let's start from W, let's start from Y. I could build this layering, the stratification over here on the right from any thing that I have. From any vertex I choose. The largest such distance is called the diameter of the graph. Now, interestingly enough, that is not the same as the longest walk or the longest path. Because remember, I can go walking back and forth between vertices over and over and over again. The greatest possible distance is the diameter of the graph, and we will call that DIAM of G. That's an upper bound on distance. No distance is bigger than that within my graph. Now that's interesting because that's the largest, shortest path, right? So it's the biggest, smallest. We'll find a lot of that sort of min-maxing idea in a lot of different places. Intro to theoretical here, and in large numbers of other types of measurements on graphs. If G is connected, DUV equals the diameter. So let's suppose these two vertices are as far apart as we can get, and I pick a third vertex, W not equal to U or V. Flip a coin, U or V. Seriously, flip a coin, U or V. V. There, I flipped the coin the other way for you. If I'm going from U to V, and that's the biggest possible distance I'm allowed to go, then going anywhere other than V can't go through V, because that would be a longer path than the diameter, and you're not allowed to have a bigger path than the diameter. There's the upper limit on your distance. There's got to be a shorter way to get there. And that shorter way is the geodesic from V to W, and therefore it avoids U. Whew. We did one proof so far. We talked about several of them, but we walked around them for the most time. 99% of the time, my problems will not actually ask you for formal proofs. They'll ask you show, explain, justify. I'm not going to want a lot of formal proofs, because as you've seen, they're not pretty. We may have to do some, but I'll try and do more of these arguments. In the textbook, the theorem I proved for you all has a converse statement. And that really means there's an if and only if statement in there. We started with if G minus U and G minus V were connected, then G would be connected. And now I'm saying if G is connected, there are two special vertices that if you pull out either one, you didn't disconnect it. It's still connected somehow. That means it works in both directions. This is actually in the textbook, I think is theorem 9. And then the if and only if combines those two and just is written down as theorem 10. But that's an interesting statement, that connectedness is literally built on more than one vertex being removable. That leads me to a bigger question further down the line. How do I figure out how to take graphs apart or put them together? And that means I need to talk about what some of the common types of graphs are. And I've got exactly 30 seconds left to do it in, so I'm not going to do it today. I'll do it on Wednesday. I will see you all on that day. Have a wonderful extended weekend. Please note that we just finished section 2 today. I didn't even start section 3, so that's what we're going to do on Wednesday. See you all then.